Hey there, have you ever just stopped and wondered how we can find anything close to certainty in a world that feels so random? How scientists and pollsters can make these incredibly confident predictions just by looking at a tiny little slice of data. Well, today, we're going to pull back the curtain on the statistics that make all of that possible. We're going to uncover the amazing logic that turns pure chance into predictions you can actually count on. Okay, let's just dive right in with the big question, right? The one that makes all of this feel a little bit like magic. How on earth can a poll of just 1,000 people, 1,000, tell us what hundreds of millions of people are thinking? It just seems impossible, doesn't it? It feels like some kind of trick, but I promise you it's not. And by the end of this, you're going to see the powerful, elegant math that makes it a reality. So where do we even begin this journey? Well, it all starts at the absolute foundation. Before we can make any of these grand statements about entire populations, we have to get really, really good at one simple thing: counting. And this gets right to the heart of basic probability. See, at its core, probability is really just a fraction. It's the number of ways the thing you want to happen can happen, divided by the total number of things that could possibly happen. And that's where combinatorics comes in. It's basically the science that gives us a system, a set of tools to figure out those two numbers, especially when you're dealing with millions or even billions of possibilities. Now, to count things correctly, you have to ask one critical question. Does the order matter? If the answer is yes, then we're talking about permutations. A good way to remember it is permutation position. Think about a password or the finishing order in a race. The sequence is absolutely everything. But if the order doesn't matter, we're dealing with combinations. This is like picking a team for a project. It makes no difference if you were picked first or last, you're still on the team. So, you see, choosing the right tool for the job is crucial. Let's bring this back to our poll. When a pollster picks 1,000 people to survey, are they arranging them in some kind of specific order? No, of course not. They're just forming a group, which means that is a combination. And just like that, we've taken our first big logical step towards solving the paradox. Okay, so we've got the counting part down. We know how to figure out the number of outcomes, but, raw counts aren't really enough. What we need now is a way to find predictable mathematical patterns that are hiding inside all of that apparent randomness. And the tool for that is something called a random variable. Honestly, the easiest way to think about it is like a translator. It takes a real-world outcome, like a person saying yes or no to a poll question, and it translates it into a number, maybe a 1 or a 0. So why to do this? It's simple, because once we have numbers, we can finally do math. We can calculate averages, we can measure how spread out things are, and we can start to spot those patterns we're looking for. Now, these random variables come in two main flavors. First, you've got discrete variables. These are things you can count, like the number of heads you get in 10 coin flips, or the number of people who say yes in our poll. There's a finite number of possible outcomes. Then you have continuous variables, which can be any value within a range. Think about a person's exact height or the temperature outside. And knowing which is super important because it determines what kind of math we can use to analyze them. Now, of all the patterns in the universe, one is king, the normal distribution. You probably know it as the bell curve. And it's just beautiful in its simplicity. You only need just two, numbers to describe it perfectly. The mean, or average, which tells you where the center is, and the standard deviation, which tells you how spread out the data is. But this last part, this is the key to everything. We know with mathematical certainty that roughly 95% of all data in a normal distribution falls within a very specific, predictable range around that average. Remember that number? 95%. It is going to be very important. Okay, we have all the building blocks in place. Now it's time for the main event. We're about to uncover the two universal laws that are the engine behind all of modern statistics. This, right here, is where the real magic happens. First up, we have the law of large numbers. This is the bedrock principle that makes sampling reliable in the first place. It's a mathematical guarantee that says the more data you collect, the more people you survey, the more certain you can be that your sample's average is getting closer and closer to the real average of the entire population. This is the law that keeps our small sample from being just a random, misleading fluke. But the real superstar of the show is the central limit theorem. If the law of large numbers tells us that our sample average will be close to the real one, the central limit theorem, or CLT, tells us something even more incredible.
It describes the exact pattern, the very shape of all the possible sample results we could have gotten. And here is where things get truly wild. Let's say the data for our entire population is completely bizarre. I mean, it could be lumpy, skewed to one side, totally random. It doesn't matter one bit. Because the most amazing thing about the central limit theorem is that it doesn't care what the original population looks like. So imagine this experiment with me. We dip into that weird-looking population. We pull out a random sample of 1,000 people, and we calculate their average opinion. We write it down. Then we do it again, and again, and again, thousands and thousands of times. We end up with this huge list of different sample averages. So what happens when we plot all of those averages on a graph? This is the punchline of all of statistics. The distribution of those sample averages will always form a perfect, predictable bell curve. It doesn't matter how weird the original data was. This is the profound insight of the central limit theorem. It tells us that randomness, when you repeat it and average it out, stops being random. It creates a beautiful, predictable pattern. And a pattern that's predictable, well, that's a pattern we can work with. So let's bring it all home. We now have all the tools we need. Let's put them together and finally, officially, answer the pollster's paradox. That one poll we took, it's just a single data point that came from that beautiful, predictable bell curve we just talked about. And because we know the exact mathematical properties of that curve, we can actually calculate the probability of how close our sample is to the real answer. We can literally put a number on our own uncertainty. You know, the formal process for doing this is called hypothesis testing. We basically make a starting assumption, like candidate A has 50% of the vote, and then we use our poll data to see how likely or unlikely that assumption is. But that can get pretty deep. So let's focus on the key takeaway here, which is how we measure our confidence. A key tool in this is something called a p-value. The simplest way to think about it is that it tells us how surprising our poll result is. If we get a tiny p-value, it suggests a result is really unusual, which would make us start to question that initial assumption we made. Now listen up, because this is probably the single biggest mistake people make. A small p-value does not prove something is true. It doesn't. It is simply a measure of how surprising our data is, assuming our starting idea was correct. And it's this idea of measuring surprise that brings us to our final answer. All of this, from counting to random variables to that amazing central limit theorem, it all leads us here, confidence intervals. Because we know from the CLT that the results follow that predictable bell curve, we can take our one poll result, build a range around it, you've heard of it, the margin of error, and remember that 95% rule we talked about? We use it right here. We can state that we are 95% confident the true unknown value for the entire nation is somewhere inside that range. And that is how a tiny sample of 1,000 people gives us a window into the mind of a nation. So, there you have it. We've journeyed all the way from simple counting to the most powerful laws in statistics. This logic isn't just for polls. It's the engine behind modern science, medicine, and economics. You now have the framework to understand it all. So the only question left is this. Now that you know how certainty is built from chance, what accepted truth will you question next?